is homework number 4, problem 1. And we have some U-Hart fraternity brothers on a road trip. And they're driving in this car at point P, and they're about to make a 180-degree turn. This thing has a radius of 250 feet. And just as they're about to enter the turn, they're traveling at 65 miles per hour. But they're slowing down. Their speed is decreasing at 6 feet per second squared. And we want to determine after 3 seconds into the curve the velocity in the xy components and their acceleration in xy components. And I'm requiring that you use a coordinate transformation array as part of this. So let's get started here. I've written out the givens, and let's go ahead and figure out how with the 65 miles per hour, go 5,280 feet per miles, 3,600 seconds per hour, and that's going to equal 95.33 feet per second. We need to do that because everything's in feet per seconds, right? Feet per second squared there. All right, so get that out of the way. Now we need to figure out whereabouts they're gonna be after 3 seconds. We could treat this this curve right here. We're gonna have that motion around that curve, and I'm gonna call that parameter S. So like the distance along that curve. We'll say that we're gonna have S. So we're gonna find that distance. S0 plus the initial velocity in the S direction, which is sort of like tangential there, times the time, plus 1/2 the acceleration, right? And this is the tangential acceleration, by the way. That's the it's that -6 times t squared. Did I do that right? I think so. We'll just say that it starts at 0. So we have 95.33 times 3 seconds plus 1/2 -6 times 3 squared. And so multiply that by 3, and that's going to be 9 times 6, so 54, divided by 2, and subtract it out, and I get it's 259 feet. And now we want to figure out what angle that's going to be. All right, so we know the radius and we know the arc length. So from that, we're going to be able to get the theta. I'll call it theta. So we're going to have this. This is really delta S over R. And the answer here is going to be in radians, right? So we have 259.0 and divided by 250. So we have 1.036 radians. But we want to have it in degrees, right? So that'd be nice. So the way we do this is we multiply it by 180 degrees divided by pi, right? All right, so we divide, like this, really think of it, 360 divided by 2 pi, right? So turn it into degrees. So 180 times, and then pi, and we divide, and we end up with that's 59.36 degrees. So that's the angle that this thing is, the car is going to be kind of in this position right there, right? So it's kind of 60 degrees, a little more like that, 60 degrees, right? A little steeper than that. Okay. And, okay. What else do we want to do? Well, we can figure out what the velocity is going to be at that time, right? So that's actually kind of pretty easy. So we'll find the velocity, say, is going to be, or speed, I should say, is going to be equal to the original velocity plus the acceleration times the time, right? So the original velocity, our speed is 95.33, and we have a -6, and then times 3, so 95.33 minus 18, it's going to be 77.33 feet per second. Okay. And let's figure out what the accelerations are going to be. So this is the, of course, obviously this is the tangential direction, right? So if we were going to have the velocity of the thing, that would be 77.33 feet per second. And okay, so if they're at 59.36 degrees right there, then their velocity, their movement, so their velocity is actually going to be the complement of that, right? So that would be 90 minus that. Did I get that right? I think so, right? So right there, that should be 30.64 degrees, right? Because their position's here, but their velocity is actually going to be perpendicular to that position right there. I think I said that right. We also want to get the acceleration while we're at this. Right? We'll figure out what these things are like in this orientation, and then we'll do our transformation matrix. All right, so their acceleration was kind of given to us in two parts, right? Well, it is in two parts. It's going to be the tangential acceleration, right, times ET, plus the normal acceleration times EN, right there. Well, this one is easy because it's going to be, and it's in the negative direction, so it's going to be a -6 ET, and and by the way, we could also have said this up here. I should have written this out. 70. Another way that we could have written this was this, and so coming back here. Sorry for the jumping around part. The AN is going to be V squared divided by rho. We're calling it R here. So we're going to take 77.33 squared divided by 250, and that's going to be EN. Okay. I will draw the coordinate axes here in a second. So that means that the acceleration is going to be, well, it's -6 ET plus this squared divided by 250. So 23.92 EN, and this is feet per second squared. All right. Now we have these in, this is in path coordinates, and this is in path coordinates right here, right? So we want to write out what those coordinates look like right here. Let's see, we'll start with an I, and it's easier to start with this I and this J. They're going to look like this, horizontally, vertically and horizontally, right there. So there's I, and here's J. Now, at this time, right, at some point later on, let's say it's going to be kind of up, like, right, let's even kind of draw it in here. Let's sketch it in here, even though this is part of the setup right there. It's going to be like this right there. That's going to be, right, at this later time right here, that's going to be our ET, and our EN. So let me draw that as darker right there. And our EN is going to be going in that direction right there. And if we're going to get the angles the right way, we'll draw that down here below. right there. And it makes it easier with the ruler right here. See, we can make this like perpendicular here. So I have ET and EN right there. When doing these, I think it makes it a lot easier to extend them as dashed lines. It helps us to figure out what angles we want to use as part of this thing, generally speaking. And if it gets close to 45, you might exaggerate it so you can figure out which one's going to be the narrow and which one's going to be the wide one. Like, we can kind of see that this right here, let's go ahead and call this theta right there. That's the angle this thing has moved at, right? That we know. That's the one that we called up here in the theta coming up right there. I know that this is the smaller one, which is close to 30 degrees right in there. But we already established this, right? So I'd also say that this guy right here, he's also theta. So when making our coordinate axis, our coordinate transformation array, let's try to make this nice and neat if I can. Yeah, something like that. Okay. And I guess I'll make it this way. Somewhere in between. I think that's the middle. Right on there. And that looks about right. All right, I like to go the I and the J on top. And then we go E, T, and E, N. All right. We start with the I. And we can see that it's going to be or we can start with the ET. Either way we want to put it in. Let's do the ET. Let's do the ET, and we can also put in the angle right there too. By the way, that might make it easier to see that this is going to be in the ET will be a negative I because it's going in the opposite direction, right? A component of ET that's I is the negative here, and it's going to be sine of because it's going to be opposite from this angle. So go negative sine of that angle. And then to go with the ET, we could also see that it's in the positive J right there, right? And it's going to be the cosine of that theta because it's adjacent right there. And then we do the same thing. Whoop, I'm sorry. I was supposed to be ET's J. Okay. We'll do the same thing for the N. That is also going to be negative I, but now it's going to be adjacent to that angle right there. So it's going to be negative cosine, which you expect. You expect these things to be opposite from each other. And then because they're negative here and negative, there's only going to be one that's positive in our array. So we can predict this is going to be negative sine, but let's take a look at it. This is EN, and sure enough, it's in the negative J direction, and it's opposite right there, so negative sine. So we've been able to make this. All right, so remember that theta is going to be 59.36. I decided to keep it right there instead of using the smaller of the angles. So now let's take the velocity. Well, the velocity is just in the ET direction, but we want it in the I and J. So we multiply whatever's in front of ET by this I and that J. So the velocity is going to become 77.33 times the negative sine of 59.36 I plus our 77.33 times the cosine of 59.36 J. And these are still going to be feet per second. So let's do the 77.33, 59.36, take the sine of it, multiply. So we're going to end up getting that it's going to be 66, whoops, it's going to be negative, can't remember that, 66.53 I plus our 59.36 cosine times positive 39.41. And we should always do like a little sanity check here and say, does this make sense? Well, they're going in the negative I direction, obviously, but they're still traveling in the positive y direction. So it's positive j. So it's in the negative x direction and the positive y direction. That makes sense. We only had to do one because it's only the tangential, but now we have to do the acceleration here. So let's see. I know that my video goes long when the screensaver starts to go on. I don't think you see that, but I do. Okay, so here's the acceleration. So we're going to take that -6, and it's tangential, and we're going to buy the negative sign of theta, and for the I and the cosine here. But let's do the i's together. Let's keep them together right here. So I'm going to say, I'm going back and forth. So I'm going to kind of like combine a step here. Hopefully this won't be confusing here. I'm going to take that -6 and multiply it by a negative sign of 59.36. And I'm going to add onto it that 23.92 times the negative cosine of 59.36, and these are both i's. And then I'm going to do the same thing for this -6 times the cosine, positive cosine of 59.36, and then I'm going to take this 23.92, didn't leave myself a lot of room, and the negative sign of 59.36. Wow, I still did it again. Darn. J. I like to stay with it. Why would they make that green line unless you were supposed to stay inside it? But and this would be feet per second squared. So really made a mess out of that. Should have planned, should have like kind of forecast, but whatever. So I'm going to take, this is a negative, so it's just going to be 6 times 59.36. Take the sign of that, multiply it, boom. So that's a positive number. But this is going to be a negative number, right? So we're going to take 23.92 and 59.36, take the cosine of it, multiply it. Now we're going to subtract that from there, so boom. So we get our acceleration is going to be a negative 7.028 I. All right, so it is accelerating in that direction. Now for the y direction, this is negative, so this is going to be a negative value, and that's negative. So this is going to, both of these are negative, right? So it's going to definitely be a negative answer in the end. So we take 6 and 59.36, take the cosine of it, multiply it. That's good. I'll make it negative, but I was just going to add it and say it's negative. But 23.92. Did I get that right? Yeah. And a 59.36. Take the sine of it, multiply it, and it's minus. So we get a negative 23.64 J feet per second squared. All right. And a sanity check. Yeah, he's slowing down. So it's actually kind of interesting here, right? It's actually coming this way right there. So even though he was slowing down, which makes it seem like it should be negative in the tangential direction, the change in direction is enough that it's kind of still making it go in the negative x direction. So the answers are going to be A, V is equal to negative 66.5 I plus 39.4 J feet per second, and the acceleration is going to be a negative 7.03 I plus negative 23.6 J feet per second squared. And what's boxing? It's just a courtesy box so the professor can find your answer. It doesn't have to go searching for it. Some people like the double underline. I prefer the box, having a box in it. Okay, so there we go. 1 down, 2 to go.